Hello, I sincerely hope that most or all of you can hear me right now. This is must admit, this is a little interesting. I'm in a almost empty room talking to a screen, but these are the times. So before we get going, first like to acknowledge the traditional territory of the Squamish First Nations, which we're not gathered on, but most of us are on right now. Just want to quickly kind of recognize that there are people who have been intimately aware of climate, of natural responses, and of resource management on these lands for a very long time. I would like to now hand it over to Karen Elliott for a quick introduction.
Thank you, Ian. Good evening, everyone, and thanks for joining us virtually. In our engagement with the community around our climate action plan, one of the messages we received was that there was a need to have community conversations about climate change, and also a real interest in hosting speakers on different topics around climate change. And so obviously we decided we would lead by example first and start with our own in-house expert, Dr. Ian Picketts. So as many of you know, Ian is a former Quest professor, and we're now lucky enough to have him with us as our manager of sustainability and climate change. So at the beginning of our term in 2018, Council created a strategic plan, and we put the environment and climate change as the first pillar in our strategic plan. We felt it was a foundation on which we had to build everything else. And in our first year of office, we prioritized the development of a new community climate action plan and also funding Ian's position. We wanted to have someone who would lead this initiative both within the district and also engage our community in the topic. So it's important for Council that, I guess, we want climate change to be about all the citizens in Squamish. We want to make sure that all citizens benefit from our climate action plan and not just a few. And we also think this is a broad community conversation because we all have a role to play, whether we're individuals, businesses, not-for-profits, or public institutions like the district. Climate change is real, as we all know, and it's already impacting our lives here locally. This year, we're spending about $7.4 million on different climate mitigation and adaptation projects. And much of this is on protecting us from the natural disasters like flood and wildfire. We're also doing other things that many other local governments are starting to look at. We're starting to value our natural assets and the stormwater services that they provide. Of course, people know that we are investing in transit and active transportation to encourage people to shift away from cars. And finally, the Community Climate Action Plan, which was adopted just a few months ago, outlines our big moves. And that will now direct our budget and actions in the years to come. So it's important that you're all part of the conversation. I encourage you to ask questions this evening, challenge some of our thinking at the district, and be really an active part of the climate transition in Squamish. I want to thank you all for being here with us virtually. I know it's not the same as getting together in a space and having that energy all in the same room, but this is a great start to the conversation, and I am happily now going to turn this over to Ian.
Great. Thank you so much, Karen. Really appreciate you taking the time to introduce this. Also, before we get going, I want to give a quick acknowledgement to the communications team. They've done a ton of work to make this happen. And over the course of these talks, we're going to be experimenting with some different tools to try to make these more interactive. We are planning to have 4 of these presentations. So this first one is going to be much more focused specifically on the science. But over the next 3, we are going to get more and more oriented directly toward our community, and hopefully with those try more and more tools to be increasingly interactive. So Karen covered a lot of this, but just a quick kind of rationale for this. One of the things that I've found difficult with COVID is it can be a little bit alienating. One of my favorite things about kind of climate and environmental action is getting together with people to learn and communicate and converse and discuss about ideas. So part of what we are trying to do is to replicate that to the degree which we can. So yeah, please try to participate in the polls. Please ask questions, chat with your friends who you're with, text your friends who you know are also listening to this presentation. Secondly, really hoping that this can be a resource, particularly for teachers. There are a lot of people in our community and other communities working very hard in adjusting to a rapidly changing job description. So maybe some teachers can use these as references and resources or required materials. And finally, we all know that climate change is a challenge, and it's important that we also challenge ourselves. So in these presentations, I'm not going to shy away from making these a little bit more difficult. You'll notice on a lot of the slides, they will be available for you afterwards. A lot of the slides have additional resources and links available. I encourage you to follow those links. However, don't worry about it too much if there's certain things that you have trouble grappling with. You don't need to master the fundamentals of energy budgets to effectively act in climate. Also, this is a humbling community to give this presentation to. There are a lot of people out there who know a lot more about much of this than myself. So I definitely want to acknowledge. Okay, so for today's talk, we're going to give a quick intro to energy and energy budgets, then go over what climate change is, what it means, how it differs from weather and variability, and then look at future climate in Squamish. Hopefully, after that, in the next couple of weeks, we can really try to unpack not just what the numbers are of future climate in Squamish, but what that means. Like what are the impacts of that, and what can Squamish do to affect a future that might be more desired. Okay, these are always pretty hard to start because climate is such a huge subject. So a very broad, bold, big entry is to ask, what is energy? A very unacademic answer to that is the ability to do stuff. It's the ability to do work. Work can be described as force times distance. Energy is really interesting and fun to work with because it doesn't change. It never really disappears, but it takes on many different forms. So different types of energy include heat, light, sound, electrical or kinetic energy, chemical energy, nuclear energy, etc. So there's all sorts of types of energy, and it's always changing type. So just one quick example is the way a light bulb works is you have electrical energy and it transfers it into both heat and light energy. A more efficient light bulb just gives you less heat energy and more light energy. Energy is measured in joules. And but if you look at a light bulb, it'll tell you how powerful it is in watts. And a watt is just a joule per second. So it's an amount of energy over unit time. So if I were to ask you what the main sources of Earth's energy is, I hope that I would be wasting my time in asking a large group of people that, because overwhelmingly, hopefully you said the sun. But there are other forms of energy that Earth gets. So we're going to have a fun quiz and encourage you to go to the poll and provide your answer. So besides the sun, what is the next most abundant source of energy that Earth gets? So please take a minute, discuss with who you're watching with, and fill out the poll. Don't worry, no one will know which answer was yours. So the possibilities are from the moon, from Earth's energy, from Earth's inner core. So that would be the nuclear decay of radioactive elements. We do get energy from other stars, much like the sun, but they're a little further away. And also there is energy amongst the universe that exists mostly from the Big Bang. So which of those is giving us the most energy? We have a few responses. No. Do you want to, what did people think? Which? Okay. All right. Okay. Might as well end it. Okay, excellent work. It is actually Earth's inner core. Again, mostly by the decay of radioactive of elements. I was also tempted to write E, this is a silly question, and you would also be correct if you selected that. Because in actuality, all of these other sources of energy are absolutely minimal compared to the sun. So we get about 99.99% of our energy, or about 341 watts per meter squared on average, from the sun, and we get about 0.06 watts per meter squared from Earth's inner core. The moon's a bit of a trick question. The energy we get actually is reflected off the sun, but we do get slightly more energy in a full moon. It's kind of an interesting fun fact. And then we do get very small amounts of energy from other stars and background radiation. All right. So I said I was going to make this challenging. So teachers might want to ask their students to figure this out on their own. But again, one of the cool things about energy is, although not easy, the calculations are simple in the fact that there are answers that you can deduce. So a challenge you can ask yourself is, how much does the sun warm the Earth? And with most of this information, you actually don't need all of it. You can come up with an answer. I'm not going to ask you to do this right now, just in the interest of time. But I definitely encourage math teachers to get their students to try to balance this equation and to come up with a result. So the way you try to figure it out is that Earth is a sphere with a certain radius, and we are getting energy from the sun that's hitting the sphere, but it's not hitting all of it. So if you see the top right diagram, you can notice that it's a two-dimensional circle is a very good approximation for how much energy we are receiving. We're obviously not getting energy at night from the sun when we're on the dark side of the planet. So that's where we're getting our energy. That's the input of energy. But Earth is also somewhat reflective, or it has an albedo. So not all of that energy is getting absorbed. Some of it is bouncing right back to space. So if Earth was a perfect mirror, it wouldn't get energy, any of the energy. If Earth was a black hole, it would get all of that energy. So the albedo of Earth is approximately 0.3. That means about 70% of the energy that comes in gets absorbed. So we're getting energy. The input is coming into a circle, but Earth is emitting the energy throughout the whole three-dimensional sphere. And back in the 1800s, a couple of physicists came up with the Stefan Boltzmann law, and they showed that the amount of energy radiated from a body is directly proportional to the temperature, to the fourth square. So you can use this really crazy constant that you can see at the bottom, and calculate, balance the amount of energy that's coming in, how much energy Earth's radiating, and figure out how warm Earth should be. So on this next page, we have the equation balanced. If you're Richard Hoshino, who might be watching, you might just do this in your head, but everyone else probably needs their calculator. And when you do this equation, you get about 253.7 Kelvin, which is about negative 19.5 degrees Celsius. So that means, based on the amount of energy we're getting from the sun, Earth should be about minus 19 degrees Celsius. If you add in those other minor inputs of energy, it should actually be about minus 18 degrees Celsius. Very fortunately, Earth is not. Average temperature is nowhere near this, and we're going to come back to that. So, on a totally unrelated note, our next challenge question for you is to think back to your high school chemistry and tell us what molecules make up Earth's atmosphere. So what are the 4 most abundant molecules in Earth's atmosphere? And just to make it easier, I put them in order. So please take a minute and select A, B, C, or D. Just testing our moderator. Check the answers here. Well, it's okay. We'll wait for a couple more. What's that? Okay, we're waiting. All right. Okay. So which was the biggest? Okay, the actual answer is C. So nitrogen and oxygen overwhelmingly make up the most of the molecules in Earth's atmosphere. And then argon actually makes up 1%. And then water vapor is a distant fourth. So here are the proportions of Earth's composition of Earth's atmosphere on this slide. And one thing you're going to very quickly notice is that carbon dioxide and methane make up a pretty small proportion of Earth's atmosphere. So what this begs the question is, what are these gases up to? What are they doing? You'll also notice that water vapor is a greenhouse gas, but you can't put an absolute percentage of it. So you have that little squiggly line. That just means it's approximately 0.3%. And the reason for that is that water vapor is continuously being created and destroyed. So it is not long lasting in Earth's atmosphere at all. Okay, so we're just going to show you a quick video. This was the shortest one I could find that tries to very quickly describe what these greenhouse gases, which are relatively not that abundant, are doing in our atmosphere. Oh.
This is MSJ Chem. In this video, I'll be looking at infrared absorbance by greenhouse gases. Carbon dioxide strongly absorbs electromagnetic radiation with a wavelength that falls within the infrared region of the electromagnetic spectrum. So here we have the electromagnetic spectrum, and you can see that infrared lies between microwaves and visible light. When carbon dioxide absorbs infrared radiation, it causes the bonds in the carbon dioxide molecule to vibrate. The natural frequency at which the bonds in the carbon dioxide molecule vibrate corresponds to the frequency of infrared radiation. On the left, we can see three vibrational modes of the carbon dioxide molecule. They are symmetrical stretching, asymmetrical stretching, and bending. Two of these vibrational modes, that's asymmetrical stretching and bending, produce a change in the dipole moment of the carbon dioxide molecule. In order to absorb infrared radiation, there must be a change in the dipole moment of the molecule as the bonds undergo asymmetrical stretching or bending. So when a carbon dioxide molecule undergoes asymmetrical stretching or bending, there's a change in the dipole moment of the molecule. This enables the molecule to absorb infrared radiation. Diatomic nonpolar molecules such as nitrogen and oxygen are not greenhouse gases. Oxygen and nitrogen only have one vibrational mode, involving a stretching and compression of the bond length. This does not create a change in the dipole moment of the molecule, therefore they do not absorb infrared radiation.
Okay, I hope you got all that. There's a lot of information there, but essentially what the presenter there was trying to explain is the greenhouse effect. So most of the energy from the sun is basically a giant fusion reactor. It's emitting a very large amount of energy, and most of it is coming to us in the form of light. And light is actually just a shorter wavelength than heat. So as you can see in the diagram, when the energy from the sun, mostly light, is coming to us, some of it gets reflected right away from clouds. Some of it hits the earth and is reflected as well. But most of it gets absorbed and re-radiated as heat, which was described as infrared radiation in the video. So light and heat are just different wavelengths. So greenhouse gases, the way they act is that they very quickly absorb and re-radiate some of that heat. And they basically they absorb it and they don't know what to do with that energy, so they spit it out very quickly afterward. And they spit it out in all directions, but a lot of that energy ends up coming back to Earth and makes it warmer. So without this, without the greenhouse effect, Earth would be about 33 degrees Celsius colder. As we mentioned before, looking at that calculation, about minus 18. Very fortunately, Earth is not about minus 18 degrees Celsius. That's about the average temperature of the coldest areas of Antarctica. Earth's average temperature is about plus 15 degrees Celsius. and that is much, much more conducive to life. -18, there might be some life, but probably not much, certainly nothing close to the life forms that we are. So without this too, we'd also get really wild swings of temperature between day and night. It would get very hot and very cold, all things that are not very good for plants and animals. A dipole moment that was explained in the video is essentially just a difference in electronegativity or a difference in charge. So you saw those different atoms in the molecules. When they shift, they create positive and negative charges. And so that is electronegativity, and light is electromagnetic radiation. So that is what they interact with. So you have nitrogen hanging out in the atmosphere, 80% of the atmosphere almost, but it's not doing anything. Both light and heat are invisible to it. So again, people say that as environmentalists that we need to fight the greenhouse effect, etc. As a matter of fact, it is a very, very positive thing for Earth. However, it's something to be noted that if you play with it, you might shift Earth's energy balance and lead to warming or cooling. So this next slide, we're not going to get into in a lot of detail, but this is a depiction of Earth's energy balance from NASA. So you get about 341 watts per meter squared on average coming in. If you remember from the first challenge question, that was 1,761 watts per meter squared. 340 is just a quarter of that. And that's just the proportion of a sphere to a circle of the surface area. So 340 just takes an average over 24 hours. So that is kind of our budget. That is how much energy is coming in. And as you can see in the depiction, some of this is getting reflected by clouds. Some of it is getting absorbed in the atmosphere. Most of it is hitting Earth and then is getting reflected as long wave radiation, which is shown in red. And there's a couple other interesting things happen, things like convection and evaporation, basically wind and moisture pulling heat away from the Earth. So here's some questions for those of you who are keen to get out your calculators and figure some things out, or for teachers who are keen to make their students do this. There's a couple really cool things about this energy budget that it's worth spending some time looking at. So again, I just kind of gave away the answer to the first point. The 340 watts or 341 watts per meter squared coming in is simply a quarter of 1,361 watts per meter squared, which is the amount that's directly, if you were at high noon, is what you're getting. And that's just the ratio of a sphere to a circle. If you look at the balances carefully, you're going to see that there's very slightly less energy leaving Earth than is coming in. So this diagram balances itself at the top of the diagram and at Earth's surface and in the atmosphere. So that you can do some addition and subtraction. You can convert all the percentages into watts and see that. But you will see that there's a very small more energy coming to Earth than that is moving away, and that is showing that Earth is out of balance and it is warming. So that is showing human influence on the energy budget. It's also a really interesting exercise to try to overlay the carbon cycle on this. So carbon dioxide is a very important greenhouse gas. So thinking of the different ways carbon dioxide gets between the atmosphere and things like the biosphere, the cryosphere, hydrosphere, lithosphere. So there's all sorts of really interesting process how carbon moves through these, and to think carefully about what some processes that humans are doing that might be fast forwarding some of these natural states. Again, very important to be very clear that the changes in CO2 and changes in climate are natural. These oscillations, they've happened to very significant amounts over time. However, their evidence shows that we are doing some things to it of late that are having inordinate effects, particularly when you think about time scale. So this next slide speaks to that. So we get really excellent paleoclimate or ancient climate records from ice cores. So here's one that shows over the last 800,000 years, and hopefully you can see that a strong majority of global temperature is explained by atmospheric CO2 concentrations. There are definitely other forces, both internal and external, but it's pretty hard to refute this interrelationship. So when there's more CO2, it's warmer. When there's less CO2, it's colder. There's other really interesting cycles. Ones that you might have heard of are the Milankovitch cycles, essentially little perturbations of Earth's orbit that change the seasonality and make Earth a little warmer and colder. The sun has solar fluctuations, so we get slightly more incoming radiation from the sun. There's about an 11-year sunspot cycle that we're aware of. But these exist, but they are significantly less important than CO2. CO2 does the vast amount of explaining Earth's average temperature. This next slide is known as the Keeling curve. So in the 1950s, Charles Keeling figured out a really good way to measure CO2 in the atmosphere. And at this point, atmospheric CO2 concentrations were 315 parts per million. So since this record has been kept as of May 18th, it's pretty neat. You can get this data in almost real time. So this is 2 days old. We are at 416.90 parts per million of CO2. And this amount is higher than it has been for the last 800,000 years. So if you go back to this last slide, we are pushing well above actually the top axis of this for CO2. These measurements are taken in Hawaii at the top of Mauna Loa. This is just a really good place to take these measurements. There's not a lot of, it's at high altitude, it's well mixed, it's in the middle of the Pacific Ocean. There's just not a lot of noise in the data. Things like if there was a coal factory right next door, it would mess with the result. So if you take the CO2 reading from the last 50 years and put it in the last 10,000 years, this puts it into a little bit better context. So we have very rapidly increased the amount of CO2 in our atmosphere. So over about the last 150 years, which is essentially a heartbeat in geologic time, we have raised CO2 levels to pre-industrial times, about 280 parts per million to over 400 parts per million. So hopefully at this point, I've had some success in establishing that the greenhouse effect is crucial for understanding the temperature on Earth. And it is absolutely necessary for a livable climate that we enjoy on Earth. Also, the very strong relationship between greenhouse gases and Earth's temperature, and the fact that greenhouse gas concentrations are increasing rapidly. Totally acknowledge that I've gone through this very quickly. In the climate change course I teach, this takes about a week to get through. So we're certainly just hitting some of the high points. There's all sorts of really interesting physics and chemistry. You can look at how the different greenhouse gases interact with heat. So how methane, for example, is a really potent greenhouse gas because it intercepts a lot of heat and spits it back. So CO2 reflects only about 1/26 the amount of methane does. Methane actually reflects way more of that, but thankfully it doesn't last in the atmosphere that long. So it's a really potent greenhouse gas, but it doesn't last that long. If you emit things like sulfur hexafluoride, they tend to stay in the atmosphere for like 15,000 years and re-emit long-wave radiation. So different greenhouse gases have different effectiveness in reflecting. Also, we have, to this point, not been talking about water vapor, which is the most abundant greenhouse gas. Okay, so this is all very complicated, but in actuality, greenhouse gases only tell about half the story of Earth's response to changing them. So we're going to try to get into that. So scientists have calculated that Earth's temperature should increase by about 1.6 degrees Celsius if we doubled the amount of CO2 in our atmosphere. However, more accurate models or more complete models that show all of Earth's processes actually show that Earth is expected to increase by about 2 to 4 degrees if we double it, with the median kind of projection being about 3. So just having molecules of CO2 and methane doing their thing in the atmosphere, we double the amount of it, should get about 1.6 degrees Celsius warmer. If we get up to about 560, actually we get above 3 degrees Celsius warmer and have a lot more uncertainty. So the reason for this is positive feedback cycles. And these are a little bit unintuitive, particularly the name. You think of the words positive feedback cycle sounds really good, when in actuality, they're not so good in nature. So negative feedback cycles happen all the time. They're really good for keeping things in check. A really good example is a negative feedback cycle is that when we get hot, we start to sweat, and that cools us down. Then if we get cold, we shiver, and this warms us up. So that is a negative feedback loop, which means as you go around, it tries to keep things in equilibrium. So it cancels itself out. But what if I had a kind of a design malfunction where if I shivered when I got hot? So this would mean that when I got hot, I shivered, and that would make me hotter, which would make me then shiver more. So as you can see, a positive feedback cycle reinforces itself and can be really bad. If that happened to me, eventually I would probably die of hyperthermia. So we're going to take a quick minute, write this down, or just chat with who you're listening to this with, and try to think of an interesting positive and negative feedback cycle that occurs both in nature and one that might occur in your own life. And you can be a little bit humorous about this. Think of something that tends to right itself in your life, and certain things that tend to kind of spiral a little out of control from time to time. So we're just going to take about 3 minutes and have a think about these. There's data from data. Oh, my Okay. Okay. We just a really good question came up. Someone asking about links to some of the study. These slides will be available right after the presentation, and most of them that have figures or diagrams have links on them. So I encourage you to look at them and just click on the links. I'll try to get this information from very well regarded sources. So a lot of the information I've used so far, for example, has been from NASA. Okay, so hopefully you had a minute to think about positive and negative feedback loops that may occur in nature and in your own life. To me, a really good example of a negative feedback loop that occurs all the time is predator-prey dynamics in wildlife. So if there's lots of deer, you tend to get more wolves, which means there's less deer, and then there's less wolves. So that's a really good example. In my own life, what should happen is when I get tired, I go to bed and I get a good sleep, and then I'm less tired the next day, and then maybe I stay up too late, and the next day I'm tired. As a matter of fact, a really good positive feedback loop in my life is coffee. So what happens to me a lot is I get too tired, which means I drink way too much coffee, which makes me more tired, so I drink more coffee and I can't sleep. So this is a good example of a negative feedback loop that I'm sure many parents in the audience are quite aware of. So again, positive feedback cycles serve to reinforce each other. And unfortunately, with the climate and the atmosphere, there are a few positive feedback cycles that that provided quite a big echo. So our next question is, which of the positive feedback loops that I've identified has the biggest effect on Earth's climate? So is it forest fires? So warmer temperatures lead to more forest fires, which lead to more CO2 emissions. Is it the snow ice albedo effect? Essentially, this one refers to the snow is almost white, so it has a very high albedo, so it reflects most of the incident or incoming radiation right back to space, whereas water has a very low albedo. So in the Arctic, for example, if you have the Arctic Ocean that's covered in ice, about 90% of the energy coming in is getting reflected right back to space, whereas if you have open water, 90% of the energy is being absorbed. So as it gets warmer, you get less ice, which means more energy gets absorbed, which means it gets warmer. The next one is the use of air conditioning. So the warmer it gets, the more people in many climates tend to use air conditioning. A lot of electricity involves significant greenhouse gas emissions, which leads to warmer temperatures, which leads to more air conditioning. And finally, atmospheric water vapor. So more warmer temperatures lead to more water vapor in the atmosphere, which leads to warmer temperatures. So just give you a minute and please pick the best answer. Where are we at? Oops. All right, we're going to hold out for a few more. $20? All right. All right. What do we have, Sandra? No air conditioning? Well, that's pretty good. Okay. So I totally led you astray with my image. As a matter of fact, by far the biggest climate feedback cycle is water vapor. So warmer atmospheric temperatures, as the temperature gets warmer, it can hold more water, which means you have more of a greenhouse gas in the atmosphere, which means it's warmer. So atmospheric water vapor is responsible for almost a doubling of the potency of greenhouse gases right away. And this is a tricky thing to explain because water vapor is a more abundant greenhouse gas. But the reason that we don't spend much time talking about it is that it has basically no life in the atmosphere. So water vapor will very quickly mirror what we do with CO2 and methane and other greenhouse gases that we can control. So it's a very quick and direct echo. Snow ice albedo is the second most important feedback cycle, and that is very largely responsible for the rapid temperature increases that we're seeing in the Arctic, for example. Other ones that I didn't include here, one is permafrost degradation. So we have a whole bunch of methane and a whole bunch of soil that is frozen, and as it gets warmer, we are releasing large amounts of methane in permafrost environments. That is one that hasn't kicked into a big degree yet, but it is in the future a cause of a lot of concern. Another one is ocean die-off. So at certain levels of heating and acidification, we could see large amounts of oceanic life, particularly photosynthesizing life, die and cease to become a kind of a sink of carbon or something that uptakes carbon from the atmosphere and become a source of carbon. So these feedback cycles are, to me, much more troublesome than the warming properties of greenhouse gases. Because what this means is that every time we emit greenhouse gases, we get this echo. And these feedback cycles actually echo each other. And so we kind of get, if we have one molecule of CO2 in the atmosphere, we get this all these different things, which is almost the equivalent of having two. The other problem is there's certain thresholds at which we might, if it's like pushing a rock down a hill, at a certain steepness of the hill, we might enter points where the rock starts to fall down on its own. For example, permafrost degradation, if we get to a point where we're melting so much permafrost that even if we decarbonize our entire economy, we might see very large increases in greenhouse. So this is a big part of the reason for the kind of the sense of urgency around climate action, is that we really don't want any of these feedback cycles to get away from us. All right. So one thing, it's always hard to start these talks because it is such a big topic, climate. But I felt like at this point it's a really good point to very carefully differentiate climate change, variability, and weather. So if you can wrap your head around this, you've successfully surpassed the President of the United States in your knowledge. So I feel good about that. But weather is essentially what is happening outside. Look outside, anything that is happening from minutes to a couple of weeks. So it's raining, it's hot, it's cold, it's windy. Climate variability is anything beyond individual weather events. So we're looking at months to decades. Climate variability is very noteworthy in this area because we're so close to the Pacific. There's a couple of big cycles of variability that affect us. A lot of people are quite familiar with El Nino. Those of you who are skiers look forward to La Nina years where it's cold and wet, where you get a lot of winter precipitation. And an El Nino year can be quite warm and dry. There's also the Pacific Decadal Oscillation that is about a 20-year return period. So you have weather, you have variability, but what we're trying to think about is climate change, which is defined as a statistically significant change in the climate, which refers to both the mean and or the variability over an extended period. So when we're talking about climate change, we need to be thinking of periods at a scale of 30 years or greater. So when something happens outside, it's very tricky. You have to be very careful to say this is because of climate change. So you can very quickly catch yourself making a statement that isn't very scientifically appropriate. So weather is happening, variability is happening, and climate change is happening on top of that. So these next couple slides I find quite interesting because in my opinion, they show pretty well how both climate variability and climate change can play. So this is an image from NOAA, from the United States government, about that's showing November 2010. So the size of the dot correlates to how different the temperature was that month from average. So you can see that the bigger the red dot, the warmer it was, and the bigger the small dot, the smaller it was. And what you can see, if you lived in Finland, for example, you had a very cold November 2010, or if you lived in Australia, you had a very cold 2010. However, if you lived in central Russia, they were probably breaking records all month long. So a good way to try to discern climate change would be to add up all of the positives and all of the negatives. And what you can see if you kind of look back at this and blur your eyes a bit is that the red is significantly more abundant than the blue. So overall, Earth was quite a bit warmer. However, there are still areas that were colder. Unfortunately, this exercise is getting less noteworthy as educationally as we get further along in time. So this is the January 2020 temperature anomaly. And unfortunately, there really isn't that much blue left on it. So what this is showing is that most temperatures over the month of January were higher than the 1980 to the 2010 baseline. So what they're trying to do at NOAA here is to be very careful. So they're comparing a 30-year average, so 1980 to 2010. They're taking the average of that for January's and comparing it to 2020. So that's how they're trying to make a statement about climate, not just about weather or variability, because of course all of those things are happening. And most of you probably have seen this before. This is an image from the last assessment report of the IPCC. So this is the global temperature change since 1850. So on the top, you can see from 1850 to 2012, definitely warmer and colder years have occurred. And on the bottom, all they've done is they've averaged the decade. So each of the last 5 decades has been warmer than the previous one. So when you're a local community and you're trying to prepare for climate change, global changes are noteworthy. They're certainly interesting to look at and to try to discern. But what's really important is to try to understand the climate in Squamish. And this is a particularly tricky task because there's a lot of factors. So one of which is Squamish's latitude. So largely related to the snow ice albedo effect, northern areas are warming faster than more equatorial areas. So Canada, for example, is warming approximately double the global average rate, and Canada's Arctic is warming by approximately triple the global average rate. So that's about, the average rate is about 1 degree since 1850. So that is affecting us, our latitude. Also, we're next to the largest ocean by far in the world, the Pacific Ocean, which is a huge heat sink. The water warms up. It absorbs a large amount of heat, so it warms up very slowly. So water warms up less quickly than the air. So Squamish's proximity to the Pacific Ocean significantly moderates our climate. That's why it doesn't get that snowy here, and typically doesn't get quite as hot in the summer as more inland areas. So it means that climate change is happening a little more slowly here. And also our very complex topography. Our proximity to the Pacific Ocean makes it's very rainy, and we are influenced heavily by some cycles of variability. Noteworthy is the El Nino cycle, the El Nino Southern Oscillations, and the Pacific Decadal Oscillation. So this makes precipitation trends really hard to discern because it depends where you're starting from, where you were in those phases. So if you picked a kind of a high PDO and a high El Nino phase to start from, it might look like there is a decrease in temperature. If you picked a low one, it might look like there's, a precipitation, or if you picked a low one, an increase. Finally, there's a very large number of small watersheds and steep topography in the area. So this makes river hydrological information pretty hard to model because they're so small, they're so tight, and they're very big. So we're very fortunate in the Pacific Northwest. There's a group called the Pacific Climate Impacts Consortium, and they did an overview of the BC South Coast. The link is on the side of this slide, and we'll put these slides up on the webpage right after this presentation. So since 1900, air temperatures in southwestern BC have increased by approximately 1.2 degrees Celsius, and winter temperatures, which are at the bottom, have increased quite a bit quicker than summer temperatures. This is noteworthy. Most areas in the world, particularly in the north, a lot of people say climate change doesn't make it warmer, it makes it less cold. You will also notice that the rate of temperature increase has been increasing since 1950. So the line from 1950 to 2010 is steeper than the line from 1900 to 2010. So the temperature is getting warmer more quickly. So our next slide, another question is, over the last 100 years, do you think that precipitation in Squamish has increased in winter but decreased in summer, increased in summer but decreased in winter, or increased or just decreased? So please take a minute, chat with your counterparts, and I'll go. The answers. 11. So the answer is actually C, but barely. So if we look at the next slide, you can see very slight increases in precipitation since 1900, but winter precipitation since 1950 has actually decreased. These are not, there's a low confidence in this number, in these numbers. As you can see, precipitation is a really hard thing to model, even a past trend, because there's so much variation in it. So one year you can have twice as much rain as the last year, and precipitation also changes from one location to the next. Pouring rain in Valley Cliff and totally sunny in Garibaldi Highlands. So precipitation is very different than temperature. It's much more variable, and it's much more spatially variable as well. So it's harder to, and it also, as I mentioned before, the cycles of variability really affect your baseline. So precipitation has generally increased globally over the last 100 years. This is partially because a warmer atmosphere holds more water vapor. Overall, there's been an increase in precipitation of approximately 5% in British Columbia, but there's low confidence in this because of the factors that I mentioned. Of course, climate change affects the phase of precipitation. So as temperatures get warmer, less precipitation happens as snow and more precipitation happens as rain. This phase of precipitation has really big implications on stream flow. So, snow gets stored until the freshet, and rain enters a river almost right away. So that has a big impact on what point of the year you have more water. So this is a slide that we're not going to have a lot of time to go over today, but there's probably well over 1 million points of information that went into to putting it together. So what we are looking at is the black line is past climate change. So based on observations around the world, this is global change to 2010, and then it's projections of future climate change to 2100. So the RCP, representative concentration pathway 2.6 scenario, is the blue line. And this is a scenario that the modelers at the Intergovernmental Panel on Climate Change put together essentially to see what it would take to get to 1.5 degrees Celsius above pre-industrial levels in 2100. Whereas the RCP 8.5 scenario is approximately 4.5 degrees Celsius above pre-industrial temperature. One thing, unfortunately, that's happened with the IPCC reports, they put them out, and every time after the assessments, people say, look at the worst case scenario, you're just trying to scare people, why are you even publishing that number? But for the first four, unfortunately, we went above the kind of the worst case scenario between them. This time we're actually a little bit below, and COVID's actually changing that quite a bit. Again, we're going to have to come back at this next week. There's just so much information here. But a couple things that I hope you can take away from this diagram is that if you look at 2050, right in the kind of halfway point, the two scenarios don't really differ that much. And that's because there's a lot of CO2 and other greenhouse gases in the atmosphere already. And regardless of what we do, short of actually actively taking large amounts of them out of the atmosphere, we're kind of stuck with that amount of warming. So we have committed ourselves to a certain amount of warming no matter what we do. Only as you get closer to 2100 do you see a really big change based on human actions. So our actions in the next 20 years aren't going to matter so much for 2050, but they're going to matter a whole lot for 2100. 1.5 degrees Celsius above pre-industrial level of pre-industrial temperatures is very different than 4.5 degrees Celsius. And over the next couple of weeks, we'll spend some time trying to kind of unpack a little bit what those kind of levels of temperature change means for a place like Squamish. The shading around the lines is just difference in the different climate models, the different results. So there's quite a bit of variation. So certain results might show that they might make a different approximation for the response of water vapor. Certain ones might show differently for albedo or precipitation. They're extremely complicated. They require supercomputers to run. So also a little interesting fun fact is the RCP, the number, so 2.6, means that we are getting 2.6 watts per meter squared extra energy in total net, if you think back to the first energy balance, where RCP 8.5 means we're getting an extra 8.5 watts per meter squared. So that's kind of comes back to the energy balance. Okay, so in Squamish, again, the Pacific Climate Impacts Consortium took a range of 30 global climate models. If anyone wants I'm happy to chat your ear off about climate models. I find them fascinating. I've been told by lots of people that not everyone necessarily does, so I've kept them short. But the median or the middle output of the 30 runs of global climate models using different emission scenarios says that Squamish will be 1.7 degrees Celsius warmer than the 1960 to 1990 baseline in 2050, with a range, so the 10th to 90th percentile will be 1.1 to 2.5. With climate projections, I really encourage you to try to take the range into account. It's a little bit dangerous to kind of put your hat on the middle value and take that as fact, because there's so much uncertainty and unknowns. The precipitation change is the median value is about 6%, but you can see the range actually goes from negative to positive. So again, there's less confidence in those. So as I mentioned before too, is climate is not just the change in means or average temperature and precipitation levels. It's also changes in extremes. So just a couple other outputs. So for sea level rise, there's significant uncertainty with this. It relates very largely to how much ice is lost and also thermal expansion. Water gets bigger as it gets warmer. So as the oceans gets warmer, they get bigger, and sea level increases because of that. That's actually the cause of most of sea level rise to date. The BC government in 2010 put out a recommendation that we plan for 1 meter of sea level rise in BC, but for 2100, and 2 meters for 2200. Those numbers have gone up very consistently in the last 10 years, and that's largely because rates of warming in the Arctic have been far larger than were anticipated. Extreme projections are quite complex, but a recent health study in the Lower Mainland had some pretty interesting projections. So the number of hot days in the region is projected to increase from 2 currently to 12 in 2050. So that's days above 30 degrees Celsius. So from 2 to 12 on average. And the wettest day of the year is expected to deliver 11% more precipitation than it does currently. With climate change, unfortunately, if you're thinking of a distribution curve, the tails of the distribution, kind of the edges, tend to change more quickly than the averages, which means that you see more extreme or unusual events. There has been some historical streamflow analysis done in Squamish, but no significant changes were found. Okay, so I hope I challenged you to think about some of the underlying science here, and some of the kind of physical principles that underlie our understanding of climate. One thing to take away from this too is a lot of this understanding is not actually very new. John Tyndall discovered the greenhouse effect, or the re-radiative properties of these gases, actually in 1860, which was a long time ago. So when people say that climate is this very new kind of phenomenon, we've understood these for quite a long time in our energy balances and models. We've known a lot about this for quite some time. But there's an awful lot of things that haven't been touched upon, and I have here just a few of the questions that we haven't even come close to answering. And these are some of the things that I'm hoping that we'll get to more in the next 3 weeks. And again, as I mentioned before, going to work with communications and try to make these more interactive. I know today has been a lot of me talking at you. Try to make kind of more opportunities for polls and people to come on and ask questions, etc. So final quiz. These are, of course, all true. So climate is always changing, and it is a natural phenomenon. So climate change is happening. It is natural, but recent climate changes are overwhelmingly shown to be caused by humans in the last 100 years. So we're seeing CO2 levels increase dramatically to levels that we have not experienced in the last 800,000 years. And we have of late seen rapid climate change, and it is expected to continue in the future. So climate change is largely explained by the kind of re-radiative heat trapping and re-radiating properties of greenhouse gases, but it also is amplified by positive feedback cycles. You have to be very careful. When it's really hot outside, it's probably not appropriate to say, wow, climate change, look at this, because then the next day when it's not so hot outside, someone will be like, so they'll think they just proved you wrong. You have to be very carefully and look at larger amounts of data and compare it to about a 30-year mean. Of course, that makes part of the challenge with this is it takes a long time to make strong statements. Therefore, it can take longer than we hope to act. Climate is not just kind of a shifting of the means. It's related to both shifts in means and extremes, and is projected to increase rapidly in the future. And of course, finally, it has significant implications for Squamish, both how we adjust or adapt to the changes that happen and what we do to take a role in being part of the solution or having less greenhouse gases in the atmosphere. So at this point, I'd like to thank you very much for your for sticking with me this far. And we've got about 15 more minutes and would love to hear some questions from the audience, those of you who are. Okay, so I think they're going to come through our moderator. Okay. And while some are coming up, if there's any material, please do not be shy about emailing me if I neglected to put a reference in some of it. I'd be happy to dig that up and provide it for you. I borrowed a lot from NASA for this. Yeah, no questions. Okay. So one thing, hopefully a question or two will pop up, but if not, we're going to have a little exit poll, which is not about the effectiveness of the presenter, but the platform. One of the things that we're hoping to do with this is to think about using it for other public engagement events. So we're very interested to hear how you found the interface. Okay, there's a comment just came up. What's that? How do I see it? Ooh, that's a great question. So that is something that I hope that we can focus on. I was thinking that the next lecture or next talk will look more at mitigation or actions that lower the amount of CO2 or greenhouse gases in the atmosphere. And the third one will look quite closely at adaptation. Big things is the district has an adaptation strategy that in 2016 I worked with them to create that outlines priorities. Big priorities for the district are, of course, sea level rise is very significant, and wildfires. Also, extreme precipitation events. So those are three big things that they're putting a lot of energy into. The district is doing really outstanding work on flood hazard mitigation. It's a really complex issue in Squamish. One of the challenges being the last thing you want to do is build this nice, beautiful wall to keep out the ocean, not thinking about the 5 rivers behind the wall. This is kind of the bathtub effect. If you're not careful, you can keep a lot of water in, and we can really mess ourselves up with that. So flood hazard management is a real area of focus and concern. And again, that's, flooding is not just a climate issue. That is something that has happened in Squamish many times. There's a lot of really excellent oral records from First Nations communities that show that when and how big different events have been. So I'd say flooding, they're really starting to look closely at wildfire mitigation. Also trying to understand water budgets. We're really lucky to have a lot of clean water here, but it needs to be managed carefully. In a lot of other areas in the world, that's a really big concern. Also health. So, those hot days, marginalized people, if there's a heat wave and there's 10 days in a row above 30 degrees Celsius, that's a big effect too. Sure. Ooh, great question. I'm a real nerd for visual stuff. So I find the NOAA and NASA sites are really good. They've put a lot of energy into their visuals. A great example is that the NOAA National Ocean Administration, the ocean kind of counterpart of NASA. There's all sorts of really recent information. So, for example, that like January 2020 graph, I find that really effective to communicate to people. It's so new. So NASA puts a lot of energy into kind of good science communication. One thing I'm always impressed about too is there's such a cool community of kind of learning and sharing of information. So if you go to YouTube and just type in NASA energy budget, there's a really good chance there will be 2 or 3 professors who just share half of their lecture and they'll walk you through the whole thing. So there's good information there. The most recent NRCan, climate change, Canada's changing climate, is quite good. They have an executive summary that's pretty long, but I think it's still about 10 or 12 pages, but that is really good information. The IPCC documents are probably the most comprehensive, but they're beasts. They're really, really hard to get through. So, but they also have put more energy there. You can look at their posters. Also, they've put out YouTube videos of their chapters, which can be really helpful. Yeah. That's a great question. So next week, hoping to think about probably all of them thinking more about Squamish. The next one, probably talk quite a bit about the climate action plan and the different kind of priorities for action in Squamish. I would like to share, they did some really excellent modeling. So to see what the sources of greenhouse gases are in the community and what different ways to get them down, what Squamish can do to be part of to hit that 1.5 degrees Celsius target. So kind of look a little bit more into human actions and how they relate to those different lines on the graph, and then also what the impacts of those different levels of changes are. So I think that will be the focus of the next 2. No other questions? All right, well, I hope if nothing else, I allowed some parents to skip bedtime. And some teachers to give some students some work. Thank you, everyone, for listening. So we're going to try this again next week at 7. And as I noted before, we're going to try to make the next ones get more and more interactive. So, more opportunity to ask questions throughout and to share information. So, yeah, thanks again. And again, communications did a huge amount of work to make this happen. All right. Thanks very much, everyone.